Welcome to AERO 2230 ProPilot 1, presentation number 10 on aircraft performance. The topics we'll cover in this presentation are defining performance, required pre-flight action, types of performance charts. We'll define and calculate density altitude, headwind and tailwind components, runway gradients and their effect on takeoff and landing performance, climb performance, climb speeds, absolute and service ceilings, cruise performance, range, and endurance. Federal Aviation Regulations Part 91-103 states that for all flights, pilots must know runway lengths and takeoff and landing data information. But if you're not going to be staying local at your local airport, if you're going to be flying to another destination, then you also need to know weather reports and forecasts, fuel requirements, alternate airports, and any known air traffic control delays. If you're just staying local and doing pattern work, then it's imperative that you study the runway lengths and takeoff and landing data information. This data is available in the Pilot's Operating Handbook or the flight manual for the aircraft that you'll be flying. Every aircraft has a POH, or a Pilot's Operating Handbook. It contains performance data for the aircraft, and it also contains charts that will help you determine what kind of performance you can expect given the conditions. The performance charts predict the performance based on things like temperature and density altitude, things that we'll discuss later. Performance is based on sea level temperature, which is 15 degrees Celsius or 59 degrees Fahrenheit, and atmospheric pressure of 29.92 inches of mercury, and 0% humidity. Relative humidity also impacts performance because it impacts density altitude. This combination of standard temperature and standard pressure is called a standard day. And the temperature and the pressure deviations from standard change air density, or the density altitude. And because density altitude has an effect on aircraft performance, it's important for you to calculate what the density altitude is on a given day. Now, the performance charts in the approved flight manual contain all the performance data that you need to predict the performance of your aircraft. They differ. Some of them are called FIMs, or Flight Information Manuals. Some are called POHs, or Pilot Operating Handbooks. But they all contain this performance data. And some of them use graphs, some of them use tables, and some of them use plotters. Density altitude, again, is a very important part of calculating aircraft performance. A combination of high temperature and high humidity and high altitude results in a density altitude higher than the pressure altitude, and that results in reduced aircraft performance. The higher the density altitude, the lower the performance. So density altitude depends on a number of factors. Temperature is one of the major factors, altitude, and humidity. Decreasing air density equals high density altitude. Think of the term high density altitude as higher altitude density. Air has reduced density at higher altitudes. An increase in humidity also raises the density altitude, makes the air less dense. So standard conditions again are a temperature of 59 degrees Fahrenheit or 15 degrees Celsius, pressure of 29.92 inches of mercury, and 0 humidity. This density altitude chart includes a table that will allow you to convert your indicated altitude to a pressure altitude, because remember, density altitude is pressure altitude corrected for non-standard temperature. So on the right side you see this table, and you see different altimeter settings. For each altimeter setting, there's an adjustment factor. So for example, at 29.92, which is standard pressure, the adjustment factor is 0. But if your altimeter setting is 30.20, then you would subtract 257 feet from your indicated altitude to get your pressure altitude. This is a density altitude chart that shows temperature at the bottom. Density altitude is shown on the left side, and then each of these lines is pressure altitude. So you determine your pressure altitude, and then you find the temperature at the bottom. You draw a line up to your pressure altitude and over to your density altitude. So let's find the density altitude for an airfield based on an altimeter setting of 29.25. Temperature is 81 degrees Fahrenheit or 27 degrees Celsius, and runway elevation is 5,250 feet. First, we need to convert the elevation to pressure altitude, and we find in the table that our altimeter setting is between two numbers here, 29.2 and 29.3. The adjustment is 579 feet for a 29.3 altimeter setting and 673 feet for 29.2. So since we're halfway between these altimeter settings, we need to interpolate between the two adjustments. So the first step is to take the numbers and add them together. So 673 plus 579 is 1,252. Then we divide it by 2 to get the halfway mark. Halfway between those two numbers is 626 feet. Then we add the result to the field elevation to get the pressure altitude, which is 5,876 feet. Next, we look at the temperature, 27 degrees Celsius, and the pressure altitude. So we draw a line for the pressure altitude, and that has to parallel the other pressure altitude lines. And then we draw a line straight up from the temperature, and then straight to the left from that point where they intersect. And that shows us what the density altitude is on that day. So the answer is 8,500 feet. And that makes sense because the temperature is a lot higher than standard, 27 degrees Celsius. Remember, hot temperatures result in high density altitude. Another factor that influences takeoff and landing performance is the crosswind and the headwind component. Every pilot's operating handbook has a crosswind component chart in the POH to help you determine what the crosswind and the headwind are before going out to take off. Taking off into a wind improves performance, and it reduces the length of the runway that you need in order to take off. But crosswinds can make controlling an aircraft almost impossible. The aircraft manufacturer determines a safe limit for taking off and landing with a crosswind by establishing a maximum allowable crosswind component. So here's an illustration of a headwind versus a crosswind. You can have a direct crosswind of 270 degrees if you're taking off on runway 18, which points 180 on the compass, or you can have a slight crosswind from 220 degrees, 220 degrees, or you may not have any crosswind but just a headwind of 180 degrees. Here is a crosswind component chart from a pilot's operating handbook, and it looks more complicated than it really is. It's very simple actually. The first thing we need to do is find the angle between the wind and the runway heading. So let's use an example of a wind at 220 or 220 degrees, and let's just say it's 30 knots. And let's also assume that we're on a runway 18, which is pointing 180 on the compass. So the difference between the wind direction of 220 and the runway heading of 180 is 40 degrees. That's your wind angle. Now we find the straight line on this table that represents that angle of 40 degrees. Each one of these straight lines is the angle between the wind and your runway heading. And then we find the circular line that represents our wind speed, and that was 30 knots. Where they intersect, we draw a line straight down to find our crosswind component. Now if I wanted to find out what our headwind component was, I would draw a straight line to the left to find that, and that looks to be maybe about 24 knots. So it's a headwind component of 24 knots and a crosswind component of 20 knots. Now takeoff distance is one of the most important performance calculations that you will be doing, and you need to do that for every single flight. Takeoff distance is influenced by how much force the propeller can exert on surrounding air molecules. And the higher the density of the air, the fewer molecules per cubic feet. So a higher density altitude is actually less dense air. So with a high density altitude, there are fewer molecules for the propeller to push. As a result, for any given RPM, rotations per minute, on the prop won't produce as much thrust. So you'll have a longer takeoff run and then lower climb performance as a result. Remember, headwinds decrease takeoff roll, so they actually increase takeoff performance. A tailwind increases takeoff roll, so a tailwind decreases takeoff performance. Generally speaking, you want to always try to take off into the wind as much as possible. And remember that runway slope can also affect takeoff choice. Another factor is the runway surface. All right, if you're taking off on a muddy, wet, or grass runway, that's going to increase your takeoff distance because of the friction caused by that surface. Obstacles at the end of the runway, like power lines, trees, especially at a grass field, can impact your takeoff considerations because you will have to be able to take off and climb and clear those obstacles. So you need to make adjustments for your landing and your takeoff distances when you have to clear an obstacle at the end of the runway. The same considerations need to be factored in for landing distance calculations. There's a landing distance chart in the pilot's operating handbook to help you determine what your landing distance will be on any given day. Landing into a wind, remember, reduces the aircraft's ground speed. So landing distance depends on several factors that include aircraft weight, temperature, surface, wind, and runway slope, just like takeoff distance. The pilot's operating handbook provides you with this detailed landing chart, which will allow you to estimate your landing distance before a flight. And here is a copy of a landing distance chart from a pilot's operating handbook. The great thing about these landing distance and takeoff distance tables is there usually is an example that will help you get familiar with the chart and how to use it. In this case, we have an example in the upper right hand corner showing an outside air temperature 25 degrees C, pressure altitude of 3,965 feet, aircraft weight of 2,814 pounds, and a wind component of 9 knots. So let's look at the example on the chart. You start at 25 degrees C on the left, and you draw a straight line up to the pressure altitude of 3,965 feet. From that point, you draw a straight line to the right to the next reference line. And then you follow the line parallel down until you reach the weight of the aircraft, 2,814 pounds. From that point, you draw a straight line to the right to the next reference line, and then you follow those parallel lines down until you reach the headwind component of 9 knots. At that point, again, you draw a straight line to the right to the next reference line, and then you follow those parallels up to get the landing distance over a 50-foot obstacle. If you follow that line straight to the right from the reference line, that's the landing roll. So again, you follow this line straight up from the temperature to the pressure altitude, draw a straight line to the right to the next reference line, follow these lines down until you get to the aircraft weight, then draw a straight line to the right to the next reference line, and then follow these lines down until you get to the headwind, follow and then draw a straight line to the right to the next reference line from that point. And then if we go straight to the right, that's your ground roll. And if we follow these lines up, this would be your takeoff distance over a 50-foot obstacle. So the ground roll would be 1,080 feet. The total distance over a 50-foot obstacle required would be 1,700 feet with an approach speed of 68 knots. Now here's a landing distance table that you might find in other POHs, and it gives an approximate weight, and then it gives sea level and standard temperature, ground roll of 445 feet at sea level and at standard temperature, and the total to clear 50-foot obstacle of 1,075 feet. And then you can see as the temperature decreases and the altitude increases, the ground roll increases as well as the total distance required to clear a 50-foot obstacle. Until at 7,500 feet and a temperature of 32 degrees Fahrenheit, the ground roll is 520 feet and the total distance to clear a 50-foot obstacle is 1,255 feet. But notice that there are also notes. These notes indicate that you must decrease the distance by 10% for each 4 knots of headwind. So in our prior example, we had 9 knots of headwind, so we would decrease the distances by 20% in that case. The second note says increase distance by 10% for each 60 degrees Fahrenheit temperature increase above standard. So above standard would be whatever is above these temperatures. These temperatures are standard temperatures at these altitudes. So if the temperature was 60 degrees Fahrenheit higher than 59 degrees Fahrenheit, which is quite hot, we'd have to increase the distance by 10%. And then the third note, for operation on a dry grass runway, increase distances, both ground roll and total to clear a 50-foot obstacle, by 20% of the total to clear a 50-foot obstacle figure. Let's take a look at the landing distance chart that we looked at the first time. Add another example just to give you a better idea of how to use it. So let's use a different example, starting with a temperature, outside air temperature of about 32 degrees Celsius. And we'll draw a straight line up from there to a pressure altitude of 8,000 feet. From that point, we'll draw a straight line to the right to the next reference line. And then we draw a line parallel to those lines in the weight chart down to 2,600 pounds. we'll assume that the aircraft weighs 2,600 pounds, and from that point we draw a straight line to the right to the next reference line. Then we follow those lines parallel in the wind component section of the chart, and we stop at our wind of 20 knots. At that point we draw another straight line to the right to the next reference line. And then we follow the lines parallel up to our landing distance over a 50-foot obstacle. And if I wanted to know what the landing roll was, I just draw a straight line to the right from that point to get a landing roll of about 900 feet in this case. Takeoff distance charts are very similar to landing distance charts. They use the same variables: temperature, pressure, altitude, weight of the aircraft, headwind component, to figure out what the takeoff roll and what the takeoff distance over a 50-foot obstacle would be. This is the chart from the Diamond DA40 Pilot's Operating Handbook. So after we determine takeoff performance, the next thing we need to be concerned about is the climb performance of the aircraft, because we need to make sure that the aircraft can climb out and clear obstacles if we have obstacles in the way. The charts in the Pilot's Operating Handbook provide us with a way to do that. So how do things like density, altitude, aircraft weight, headwind component, and aircraft configuration affect climb performance? Just like they actually affect takeoff performance. The higher the density altitude, the lower the climb performance. The heavier the weight of the aircraft, the lower the climb performance. More of a headwind leads to increased climb performance. And aircraft configuration, if you have your flaps down, you're going to get better climb performance, at least over the short range. Climb speeds make a big difference in climb performance. And the speed that you choose to climb out depends on your goal. If your goal is to get as high as possible in a short distance, then you want to use best angle of climb speed, or Vx, which is slower than the best rate of climb speed, Vy. Vy is the best rate of climb over time, but the best rate of climb over a distance, a given distance, is Vx. So how high can an aircraft possibly fly? Aircraft are limited to certain altitudes because of weight, power available, and density altitude. There are two terms that you need to remember. Absolute ceiling is the altitude at which the airplane can no longer climb. The climb rate at the absolute ceiling is 0 feet per minute. Service ceiling, on the other hand, is the altitude at which the aircraft can still climb, but only at 100 feet per minute. So the climb is very low, climb rate is very low at the service ceiling, and then eventually you get to the absolute ceiling where the climb rate is 0 feet per minute. Cruise performance is another calculation that we need to do to determine our power settings, manifold pressure, RPM setting. If we have a fixed pitch propeller, then we need to know what RPM to use. And we need to decide whether we're going to use 75% power, 65% power, or 55% power, and what fuel setting we want to use, either best economy or best power, to determine our fuel flow. In some cases, these cruise performance charts will provide you with your true airspeed. Range is something that you want to determine as well. Range is how far the aircraft can fly. Based on the fuel and the fuel burn, it's the furthest distance. The best range is the furthest distance that the aircraft can fly, given those factors. Nice thing about the G1000 in the Diamond DA40 that MTSU flies is that it gives you range circles on your multifunction display, so you can actually see your range on the map. Again, range is just about the distance that the aircraft can fly. And that depends on several factors. That depends on the amount of fuel that the aircraft has, the fuel burn, and also the wind and the ground speed. Now we need to distinguish between range and endurance. Endurance is simply the amount of time the aircraft can fly. It has nothing to do with the distance or the range the aircraft can fly. And that strictly depends on the amount of fuel and the fuel burn. Now we can calculate our fuel burn using the cruise para settings table in the pilot's operating handbook. Fuel consumption depends on a number of factors. They include altitude, wind, temperature, and power setting. And fuel consumption can be calculated using these tables in the pilot's operating handbook. Let's look at an example. We'll assume that we're flying on a day that's colder than standard. Let's just assume that the temperature is 20 degrees colder than standard. So we'll use the column on the left labeled ISA minus 20. If we were flying on a day closer to standard temperature, we'd use the table in the center. And if we were flying on a day that was closer to 20 degrees hotter than standard, we'd use the table on the right side. If you take a close look at the table, not only do you need to determine the temperature as it's related to the standard temperature, but you also have to determine your pressure altitude. So let's look at an example. Let's try to estimate the fuel consumption for a 500 nautical mile trip under the following conditions. Pressure altitude will be 4,000 feet, and the temperature at that altitude is 29 degrees C. The wind is calm, and we'll look for a manifold pressure setting of around 21.3 inches. First, we need to find the variation from standard. We know that the lapse rate is 2 degrees per 1,000 feet. In other words, as we climb in the atmosphere, the temperature should decrease by 2 degrees C every 1,000 feet. We'll be flying at 4,000 feet, so the temperature should decrease 8 degrees C from the surface to 4,000 feet. Now we need to find the standard temperature at 4,000 feet. The standard temperature at the surface is 15 degrees C. So all we have to do is subtract 8C from that to get the standard temperature at 4,000 feet of 7C. And then we can see the difference between the actual temperature at 4,000 feet and the standard temperature by subtracting 7C from 29 degrees C. And we find that the temperature at 4,000 feet on that day is 22 degrees hotter than standard. So that tells us to use the table on the right side. So let's take a look at that table. Now we can find the pressure altitude of 4,000 feet, and on the right we can see that our fuel flow will be 11.5 gallons per hour, and our true airspeed will be 159 knots. These are two figures that we need to solve the problem. What we can do is take the total distance of our flight and divide that by our true airspeed. That's how fast we will be flying. And we come up with a time of 3.14 hours. And then our fuel will equal our time times the fuel flow. We determined that we would be burning 11.5 gallons per hour. So we multiply 3.14 times 11.5 to get a fuel flow, or a total fuel of 36.1 gallons for the trip. That's the end of the presentation on aircraft performance. But I highly recommend that you watch the videos posted on D2L to help you determine pressure altitude, density altitude, figure out wind components, takeoff distance charts, climb performance charts, and using the engine power and true airspeed charts. The next presentation will be on weather products and services.